Hi, welcome back. In this video, we're going to talk about how to graph polynomials. Now, in the previous few videos, we've been talking about how to factor them, right? How to look at it in factor form, whether it's a cubic or a quartic, right? How do you factor polynomials of degree x to the third or higher? Here, we're going to talk about the factored form and the standard form and what to look for in different formats and how to go about graphing them. So let's get right to it. So first we're going to focus on the leading exponent and the leading coefficient, right? If you have a general polynomial, say something like this, x to the fifth plus bx to the fourth plus cx to the third dx squared plus ex plus f. Some general polynomial. The leading exponent is the highest exponent. That's this number right here. And the leading coefficient is the number that goes in front of our highest exponent. So we're going to be focusing primarily on this component first. Knowing the highest exponent of a polynomial, whether it's to the fifth, to the fourth, right? And whether the number in front of it is positive or negative will tell us a lot about the graph. Now, to do this, we're going to start with some basics. Let's look at y equals x. If we go back to algebra 1, right, our graph will look something like this. And what happens if y was a negative x? Well, the graph would be pointing downward. Yeah. Let's look at a quadratic, y equals x squared. If it's positive, it'll be pointing upward. And if it's negative, it'll be pointing downward. So this value in the front, right, the leading coefficient will tell us if the function is pointing up or pointing down. That's the first component. If it's positive, sometimes it'll have both arrows pointing upward, or sometimes the function will increase in the long run. Right? Now, what does the leading exponent tell us? The leading exponent will tell us how many changes or turns the graph is going to go through. Right? So if we have, say, here we have x. There's only one x value, so technically the exponent is 1. Notice how it only goes in one direction. There are no changes to the line. It's just a straight path. Here we have 2 as an exponent, which means there's going to go through two paths. It's going to go through here and through here, right? There are two different directions that the function is going to be moving through, whether it's going in this direction and then the other direction, right? So let's look at this in terms of like the number of paths that the function will move through as you're drawing your graph, right? What is it going to do? So let's look at, say, cubic, x to the third. That means that the function will go through 3 different paths. It'll say start up. This is our first path. And then it's going to change directions. Say this is the second path. Right now it looks like a quadratic, right? Something like this. And then if it changes directions again, it'll change it to our third path. This is sort of what a cubic function would look like. Now, since we have a positive number here in the front, and the function is, in the long run, going to be pointing to the positives, we say this is a positive x cubed. Negative x cubed would say that the function is going to decrease over time. It'll go through one path, 2 by changing directions, and then it'll change directions again, but notice how the graph is now trending towards the negatives, as opposed to here it was trending to the positives. Yeah. Let's look at, say, x to the fourth. This has to go through 4 different changes, right? So let's say that it's going this way. We start with the first path. 1, 2, it starts going up again. Change paths again. 3, and then change paths again. 4. Notice how both arrows are pointing up, like the quadratic, right? When it's positive, both arrows are pointing upward. Since both of them are pointing up, we have a positive coefficient here, positive 1 x to the fourth. But what would a negative x to the fourth look like? Well, now I know that the arrows have to be pointing downward, right? This is the first part. It's going to change directions. That's 2. Change directions again. That's 3. Change directions again. That's 4. So this one looks more like a W. This looks more like an M, right? But notice how there's a trend here. Here we're dealing with odd exponents. What do we notice about the arrows? They're always pointing in opposite directions. It's pointing up, pointing down, pointing up, pointing down. Right? So whenever you have an odd exponent as a polynomial, when the highest degree is an odd exponent, the arrows are going to be pointing opposite direction. One's pointing down, one side is pointing up, or vice versa, right? Now, notice how when the exponents are even, like 2 or 4, the arrows will always be pointing in the same direction. So the arrows are both pointing up, or maybe they're both pointing down. Yeah, so something like x to the fifth, or x to the sixth, if you're looking at those sketches, right? It's going to go through 5 changes. 1, 2, 3, 4, 5. Notice how the arrows are pointing in opposite directions. And to the 6th, 1, 2, 3, 4, 5, 6. To the 6th power, it's going to be pointing in the same direction, right? When the exponent is even, it'll have an even number of paths it's going to take. And when it's odd, it'll not be even, so it'll go in different directions. So knowing this really tells us, and it paints a really good picture as to how to look at a general situation, right? So let's try that with this right here. Let's do a couple examples and see what that would look like in standard form. This is what we refer to a polynomial in standard form. Yeah, I'll show you an example of standard form, and then I'll show you one in vertex form so you can tell the difference. Okay, so here I have it in standard form, and I'm going to look at and identify the leading coefficient and the leading exponent. This is x to the fourth power, so there's going to be 4 turns on the graph. It's going to go through 4 different paths. Yeah. I also know that in front we have a positive 1. So I know that because it's even, both arrows will be pointing in the same direction, and because it's positive, it's pointing up. And it's going to go through 4 different paths. So let's do something like this. 1, 2, 3, 4. This is the first path. It's going down. It changes direction. That's 2. Changes direction again. That's 3. Changes direction again. That's 4. So it's an x to the fourth power, and because it's positive, the arrows, both arrows, are pointing upward. Yeah. What about this one? Here we have a negative leading coefficient and a 3 as the third power. So it's going to go through 3 changes. Because it's odd, the arrows will be pointing in opposite direction, right? Opposite to each other. And it's going to be going negative, so it's going to have to point down on the long run, right? It's going to look something like this. It's trending to the negatives. That's what this tells us, right? The arrows are pointing opposite direction. This is the first path, 1 down, change direction, that's 2. Change direction, that's 3. Now there's actually something else that we can do with the sketch. We can actually also look at the y-intercept. This notation, standard form, also tells us the y-intercept. And I want to invite you to think about, what do we know about all y-intercepts? Well, regardless of where it crosses the y, 0 will be the input. The x value will always be 0. Maybe it's down here where y is negative. What's the x value going to be? Also 0. So if we're plugging 0 for all of your x's, this turns into 0. This turns into 0. 0 squared times 2 is also 0 plus 0, and you're left with plus 4. That becomes my y-intercept. Yeah? So a polynomial in standard form, whether you're dealing with a line, y equals mx plus b, whether you're dealing with a quadratic, or a general function like x to the 4th, bx cubed plus cx squared plus d. Right? The constant will always represent the y-intercept. So if I were to draw a sketch here, I could sort of say something like this. Maybe this is my graph. 1, 2, 3, 4. Maybe it crosses through 4 on the y-axis. And it has 4 different paths it takes while going through 4 as your y-intercept. Now, if negative 2 on this other problem is my y-intercept, yeah, if it's my y-intercept, then this function has to go through, say, negative 2. And maybe it can look something like this. 1, 2. Right? So standard notation allows me to figure out the general view of the graph, right? How many turns and changes it's going to go through, and it also helps me with my y-intercept. Right? It tells me a lot in standard form. Now, vertex form will tell me something else. Vertex form is when we take this function, right, and we take the rational root theorem, like the previous few videos where we factor it, and we want to find it in factored form. This is what factored form would look like. You have found the factors, right? You can tell here that we have x plus 3 times x minus 2 times x minus 2, because there's 2 of these, right? The function, after factoring it, turns into this. Factored form. Factored form tells me a lot. It tells me several things. One, it's going to tell me the x-intercepts, and it's going to tell me the multiplicity, which I will explain here in a second. Now, before we begin, I do want to show you how this function has x times x times x. This function is generally in x cubed. It's like the general polynomial that we're working with is x to the 3rd power. Now, because the coefficients are all positive, like positive x times positive x, we're dealing with a positive x cubed. So I already know that my graph will look something like this. Yeah? All right, so our goal is to sketch a graph that looks something like this that goes through these factors. Now, whenever we're finding the x-intercept, which is the first thing we want to find, right? Whenever we look at the x-intercept, what do we know about the y value? Y value is always 0. Whether it's negative x, the y value is 0. So we're going to set this function equal to 0. To find the x-intercepts, we're going to set each of the factors equal to 0. So when we set that equal to 0, and since this repeats, we can just set it one time, we're going to solve for x. By moving the 3 over, we're going to get an x-intercept of negative 3. And here, by moving the 2 over, we have an x-intercept of positive 2. So this function has 2 x-intercepts, and it's going to look like this. So let's graph it. Let's graph 1, 2, 3. Negative 3 is an x-intercept. Positive 2 is another x-intercept. And we have to make the function look like this as we're graphing it. Now, how do we know what's happening to the function? Well, this is where we get to the even and odd multiplicity component. When we refer to multiplicity, we are talking about the number of times, right, that a factor is being repeated. How many times does x plus 3 occur? Well, it only happens once. Technically, it has 1 as an exponent. This is an odd number. Here, x minus 2 happens twice. This is an even number. Okay? Whenever we have an odd multiplicity, meaning the factor repeats 1 time, 3 times, 5 times, right? Whenever the exponent is 1, we're going to say that at that x-intercept, the function will go through the x-axis. Whenever the function has even multiplicity, like right here, x minus 2 squared. This factor is being repeated twice, right? When you find x equals 2, you're going to have 2 of those x-intercepts. Now, it can only cross the x-axis 1 time, but if it's happening twice at that location, we're going to say it's going to bounce at the x-axis. And I'll show you what I mean here in a second. Now, we know that the graph is going to look like this. It's going to point up on the right side. It's going to point down on the left side because it's going to follow that path, right? But notice how here at x equals -3, we have an odd multiplicity, meaning the root happens only 1 time. So we're going to go through the x-axis. Whenever it touches the x-axis, we're going to go through it, that location. Right? It's going to go through the x-axis. What happens at x minus 2? So when x equals +2, right here, right? Because we have an even exponent or even multiplicity, it's going to bounce at the x-axis, meaning it's going to create a bit of a curve like this. It's not going to go through the x-axis going downward. It's going to bounce back up in the other direction where it came from. And then all I can do now is connect these two lines that are up here. And now you can see how it follows the path. It goes up once. This is the first path. It changes directions down to 2. Changes direction again, and it goes up to 3 in the positive direction. We have a positive x cubed, where here it goes through the x-axis, and here it's going to bounce at the x-axis. So the multiplicity is very powerful. It tells me the behavior of the function at the x-intercept. What is it doing when it gets to the x-axis? Is it going to go through it, or will it bounce? So let's try a couple examples. We're almost done here. Let's do a few graphs here so you can sort of see how this all comes together in factored form. Yeah. All right, here we have 2 scenarios. We're going to look at this general equation, right? We can find for these, we're going to look for the x-intercepts, and we're going to look at the multiplicity. Those are the 2 things we're going to focus primarily while looking at the general picture, right? What is the general graph going to look like? So here we have 2 x's, right? X minus 3 is twice. We have another x and another x, which is a total of 4 x's. This is an x to the 4th kind of problem. This polynomial has a 4 as a degree, right? And if you're having trouble with this, you can also think of this as x minus 1 times x minus 3 times itself twice. Right? That's what the square represents. And then the x minus 5 happens once. How many x's do we have? X times x times x times x gives us x to the 4th. Now notice how the leading coefficient of x is +1, +1, +1, +1. That's going to give us a positive x to the 4th. So my graph in general will look like a positive quartic, positive to the 4th power, where there's 4 different paths it's going to take. 2, 3, and 4. And because it's positive, it's pointing up. My graph right now, or in the end, will look like a W of some kind. Okay, now let's find the x-intercepts. This one repeats. This one turns into x equals 1, right? Once you set it equal to 0 and you solve, it's going to move to the other side to become +1. This one turns into a +3, and this one turns into a +5. So I can start by graphing the x-intercepts. 1, 2, 3, 4, 5. I have an x-intercept here, 1 at 3 and 1 at 5. So since they're evenly spaced, very symmetrical picture, right? Now our graph will have both arrows pointing upward, so I can extend this going up. And I just have to figure out the middle portion of the graph, right? All those wiggles, all those different paths it's going to take. It's going to go through 4 different directions. So what happens at x equals 1? Well, how many times do we have that? We only have 1 as an exponent. So we say this is going to be odd multiplicity. The 2, this happens twice. This is going to be even multiplicity. And then this one happens only once, so we say it's odd multiplicity. So what does that mean? Well, at 1, because it's odd, it's going to go through the point. It's going to go right through it. At the x-axis, it'll go through because it's an odd exponent. Here it happens twice, which means at that location, at x equals 3, it will have a bounce. It'll bounce at the x-axis. This says bounce. This is bounce. Let's just pretend that there's a O-U-N-S-C there. Right, and then what happens at x equals 5? Because there's only 1, the odd multiplicity tells me it's going to go through the graph. So this one, it's going to go through the graph. Since both lines are already in the bottom, I can predict that the bouncing will happen below the x-axis. I have the 3 behaviors. I just have to connect the points now. And we get our W that we were looking for. Right? Key thing to look at is that it goes through that point. It goes through this point, and it bounces right here. It doesn't cross the x-axis. It's going to bounce back to the other direction, all while pointing up and making a W because it's to the 4th power. Right? So this is like the culmination of everything we've been talking about. All of our previous examples leading really up to this. Why don't you give this one a try? What does this look like? Well, what's the general graph going to say? We have 2 x's here, x squared, 1x, and then another 2 x's. That's x squared, plus 1, that's x cubed, plus 2 more, that's x to the 5th. So 5 different paths the graph is going to go through. And notice how the leading coefficient is negative. It's a negative x to the 5th. So it's going to eventually point down to the negatives while going through 1, 2, 3, 4, 5 different paths. This is what my graph is going to look like. Yeah? All right, let's sketch the graph. What are my x-intercepts? Well, this one turns into x equals negative 3. This one becomes x equals negative 1. And when I set this one as equal to 0 as well, it turns into positive 5. I have 3 x-intercepts. 1 here, and 1, 2, 3, 4, 5, and 1 here. I know the graph is going to point up on the left, point down on the right, and now I just have to figure out all of the curves that happen in between. So the multiplicity again tells me when it's even, it's going to bounce. When it happens once, it's going to go through. When it happens twice, it's going to bounce again. So at negative 3, which is 1, 2, 3, it's going to bounce. It's going to create this kind of scenario. Yeah. At negative 1, which is here, it's going to go through the line. And then at x equals 5, it's going to bounce again. Since it's below the line, it's going to bounce this way. Now I just have to connect the lines, right? I have 2 lines that are above the graph, so I'm going to connect these. Just kind of smooth it out. And these 2 below the graph are going to connect as well, which is going to just smooth it out. Notice how we have our directions, right? We have 1 here. It changes directions. It's 2. Changes directions again. This is 3. Changes directions. It's 4. Changes directions. It's 5. X to the 5th. And because it's negative, it's pointing down. The important portion here is that it's going to bounce on the x-axis. It's going to go through the x-axis. And it's going to bounce again. Just like we said it would. The thing about these sketches is that you're just going to have to trust yourself, right? Find the x-intercept. Find the multiplicity, whether it bounces or goes through. And then identify what the general picture is going to be. Draw a sketch before you even begin. Is it pointing up? Is it pointing down? How many wiggles does it have? That kind of stuff. And then when you put it all together, I recommend using a pencil so you can erase and, do your thing. When you put it together, it'll look something like this. All right, guys. Please let me know if you have any questions. Don't forget to like and subscribe. And as always, we'll talk to you later.